welcome to chapter 3.4. This is the chapter where you start getting familiar with a lot of important different kinds of functions. And finally, after we do the first, right, the library of functions, we're going to describe and talk about different kinds of very common functions in algebra. Then we're going to talk about piecewise defined functions, which is very important in college algebra. So I noticed that what I normally do, if this were face-to-face classes, I wouldn't spend all this time going through every little detail. But since I'm recording this, I think I'm going to do it. And then this would be the important stuff as well. This is very important, piecewise. But I will, before I go any further, actually, because what I normally do is instead of doing all this explanation, I just show everybody. I give everybody a copy of this picture, and I just start going over it briefly. So I want you guys to see this quickly. You will have all this sent to you, so you'll be able to review this instead of actually looking at all the graphs at once. I mean, one at a time. This is all the graphs at once, obviously, and I want to just show you quickly what they look like. So I want you to look at the what they call the identity graph, or the linear equation. These are all known as parent functions, by the way. Okay. The linear equation is just a line, okay? The parent function is y equals x. The important thing about it is that the domain and range are all real numbers. Then you move on to the quadratic function that we talked about already. It is the drawing of the parabola, that U drawing. It's a curve, right? What's important about the quadratic function is its parent function is even. Oh, I forgot to mention that the parent function of linear is odd. The parent function of the quadratic is even. So it's in its normal natural state, it's an even function, but it can also be turned into a different, if you mess with it, it won't necessarily have to be even, but normally it's even. We're going to learn about transformations next section, 3.5. The domain of all polynomials, which quadratic is a polynomial, is all real numbers. And the range, however, is not all real numbers. The range is, it starts here. We call this the vertex, and then it goes up in both directions, right? So it's from 0 to infinity. That would be the range. This is the cubic function. You notice it looks like it kind of looks like the parabola, but that this side got shifted down, right? You're thinking, why did it do that? Because now when you take a negative and you take it to the third power, it stays negative. So negative 1 to the third power is negative 1. Negative 2 to the third power, negative 8, I believe. 1, 2, 3, 4, 5, 6, 7, 8. So it's way down there. Okay, whatever. So the point is, it stays negative when you take a number to the third power. So that means it has the advantage that it has all real numbers for both domain and range, just like the linear equation. Okay. The next one I want you to see, although we're not going to work with this until chapter 6, are the exponential functions. Exponential functions simply mean an equation like this, like y equals 2 to the x power. Now the variable is an exponent instead of x to the second power, which is a polynomial. This is now considered, well, that's particular, x to the second power is quadratic, but it's type of polynomial. This is considered exponential because the exponent is where the variable exists. And now the graph starts looking like this. It's a curve again, obviously, but it has, now we introduce this concept of asymptotes. Okay? An asymptote just basically means that the graph will never actually reach a particular line. It can be a vertical asymptote or horizontal. This is an example of horizontal asymptote. If you were to zoom in and zoom in and zoom in, the graph actually never reaches the x-axis. Okay? We'll talk more about this in chapter 6, but as you can see, the domain is all real numbers. It goes from negative infinity to the positive infinity. But the range is from 0 to infinity. It never actually reaches 0, so it's not including 0, but it does, think of it as starting at 0 and going up. So it's going up to infinity. Now, another example would be that we have to be familiar with is the rational or reciprocal function or inverse function, however they want to look at it. They're going to call it the reciprocal function on your textbook, so we'll call it reciprocal. It basically looks like two curves, right? And there's one in a positive first quadrant and one in a negative fourth quadrant. So it makes this an odd function, as you can tell. And a domain and range are different because you can't equal to 0 for x or for y. It has both a horizontal and a vertical asymptote that it never equals. So we say that the domain restriction is 0. You can't equal to 0 for x, but the range restriction is 0. You can't equal to 0 for y as well. So how do you describe it can't equal to 0? You do it this way. You go anything to the left of 0 and anything to the right of 0 is part of the domain, and the same is true for the range. Okay, very important that you we're going to do this for sure in chapter 5. And yeah, chapter 5. Greatest integer is not really part of this class, but you can see if you like. This is a situation of always rounding down. This is a very common example of, let's say you have 2 point, whatever. Let's say you need to paint a wall, whatever, and you have 2.9 gallons. Can you paint? How many walls can you paint completely? You can only paint 2 walls completely, because 2.9 gallons is not enough for 3. Even though it rounds up to 3, greatest integer is always going to round down because it's not exactly enough to get you over that threshold, right? That's the idea. You don't have to worry about that. That's not going to be a part of this class. This is the constant function, this horizontal line. This, we're not going to have to worry about the inverse squared. Although, yeah, I mean, we're going to see it, but I'm not going to be making a big deal about it. Logarithms also in the class. You're going to do this later in chapter 6. That's what it looks like. It's the inverse of the exponential. We'll talk about that later. Here's a cube root function. Here's a square root function. Very important. These two functions are very important for this lesson. And obviously the absolute value is the v. So we're going to actually, instead of me just, briefly doing that, reviewing that chart, I'm also going to go ahead and do this with you guys. So we're going to discover everything we just described. So identity function. They call the linear function the identity function. You're going to see why later. It's used for identity. So we'll say, and it's identity because we're saying x equals y, which means that they're the same, right? So if x is -2, y is -2. If x is -1, y is -1. It's perfectly equal. They're identical. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. So if you plot those points, it's going to look like a straight line like this. You know what I mean? It's a perfect diagonal. So the domain and range, we talked about this, is all real numbers. I'm hoping they want it here. Oops. For both all real numbers, the x-intercepts and the y-intercepts are both the origin. It has an odd symmetry. Now this is interesting. They're asking for increasing, decrease, so we might as well go over that. If you notice that the linear function is, in at least the way it's the parent function of it, it's always going up, right? It's always increasing. It's never decreasing. It's always going bigger and bigger, bigger and bigger and bigger. So the interval of the function is decreasing. It's never decreasing, but it's always increasing. So from -infinity to infinity, it's always increasing. It does not have a local min or max, and it does not have an absolute min or max. Okay, you can see that, right? Goes up forever, goes down forever. So let's move on. The x squared function. This is the quadratic. So we're going to plug in x into this equation. So -2 squared is +4. -1 square -1, you get a +1. Square 0, you get 0. Square 1, you get 1. Square 2, you get 4. So 0, 0, 1, 1. 2, 4. -1, 1. -2, 4. So it's a u. We described it earlier, right? So what that means, if you see it, it curves, right? It doesn't go straight. It has a curve to it. The domain is always all real numbers for any polynomial. So it's all real numbers. The range, if you notice, it's not all real numbers. It starts at 0 and then goes up, right? So we say it starts at 0, including 0, right? It's actually equal to 0 at the vertex. And it goes up forever. The vertex is just that point where it starts, right? You can think of it as like the center of the u, or the bottom of the u, whatever. The x-intercept and y-intercept happen to both be the same. It happens to be the origin, so we're going to just go ahead and write that. It does have symmetry. It's an even function, okay? The graph actually decreases and then increases. So check this out. It decreases from -infinity. It goes, if you think of it from left to right, that's how you read a graph, right? It's going down, it's going down, it's going down until it reaches 0. So it's from -infinity to 0, it's decreasing. Then it starts increasing, starts going up and up and up forever from 0 to infinity. To have a local min or max? Yes, it does. It has a local min or max. I'll just highlight what it has. You know what? I'll just put it's only asking for local maximum, minimum. It's not enough space. I'm just gonna put local min at, you know, at x equals 0, and absolute max, absolute min, because it doesn't technically say, and then no absolute max. And here we'll say no local local max. Oh, that makes sense. You guys can see that. So the next one, x cubed, the cubic function. Again, we're going to plug these numbers into that equation. X cubed in this case. Negative 2 to the third power is actually going to be negative 2 times negative 2 times negative 2. It gives you negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. The graph looks like this. So 7, 8, way up there. And then negative 1. Something like that. Okay? That's the cubic function. Domain is all real numbers. Range is all real numbers. The x and y intercept are the same. It's the origin point. It has odd symmetry. So the graph is always increasing from left to right. If you think of it, the graph is always climbing. Always. Oops. I meant to get the green. There. Always climbing. If you notice, the graph is never decreasing. It's just always climbing. So it's never decreasing, but it is always increasing. By the way, we call that a monotonic function because it's always going up or always going down, whatever. So it's increasing monotonically. Local max or min, it doesn't have any of that, and it doesn't have an absolute min or max. So we're gonna just scratch that out. The next one that you care about, the square root function. Interesting, because you cannot square root negatives, so it doesn't have an answer. So you put 0, you know, whatever. This means no solution, by the way. That's empty set. And then we have square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. So it starts at 0, 1, square root of 4 is 2. It looks like that. It's just the upper part of an arc. It kind of looks like a parabola sideways, but it's just missing the bottom piece. Okay, that's what it looks like. Okay, so remember, it starts at 0 and then it curves up like that. That's terrible. There you go. There you go. So that the domain is, it's starting at 0 and then forever to the right. So from 0, including 0, to infinity. The range is also starting from 0 and going forever up. So the range can be said to be the same as the domain, which is 0 to infinity. Okay. X and y intercepts are the same. It's the origin. It has no symmetry. Doesn't have even or odd. And the function is always increasing. But it starts at 0. So we'll say from 0 to infinity. Oh wait, that's decreasing. It doesn't decrease ever, but it's increasing from 0 to infinity. And it has no absolute, local min or max. It does have an absolute min though. We'll say absolute min at x equals 0, no absolute max. We'll just say, write that in. The next one is the cube root of x. So the cube root of a negative actually does have a solution. Not like this one up here that I have to put empty set. It does have a solution. The cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. The cube root of 0 is obviously 0, 1. Cube root of 8 is 2. We're going to plug those numbers in. So here's 0, 0, 1, 1. X8 is like way out here, and then the answer is 2. So it looks something like this. It increases slowly. It does increase forever. And then this one looks like that. Like a giant S. So domain and range, believe it or not, are all real numbers for both. It's very important you keep that in mind because even though it's increasing slowly, it's still always getting bigger. And if you look at it from this point of view, it's always going down, even though it's going down very slowly. The x and y intercept are the origin points. Okay. It has an odd symmetry. This is an increasing forever function because if you think about it, it's going up ever so slightly from left to right. It goes up pretty fast here, but then it goes up slowly. It's always going up though. It's always going up. So it's increasing forever. So from negative infinity to infinity, but it's never decreasing, and it has no local min-or-max and no absolute min-or-max since it's always going up. And it's always going down if you look at it from the left point of view. Okay, the reciprocal function. This is literally just, dividing. So like 1 divided by -2 is -1/2. 1 divided by -1 is just -1. 1 divided by 0, impossible. 1 divided by 1 is 1. And 1 divided by 2 is 1/2. Let's plot those points quickly. So we're going to have 1, 1, 2, 1/2. And then I'm going to put 1/2, 2, so I know this is a point. So it looks like this. That looks terrible. It's going to be a curve. Oh my gosh. Curve. Whatever. And then it has the same thing going on here. So it curves down. It looks like that, pretty much. It looks something like that. Guys, it's not perfect, I know, but I hope you got the idea. It has a horizontal asymptote, which is the x-axis, and let me put that in red. And it also has a vertical asymptote, which is the y-axis. So there you go. Domain and range. So x cannot equal to 0. If you have it in set builder notation, you would just say x cannot equal to 0. Or y cannot equal to 0. But how do you state that in a positive form? Like, how do you say that in interval notation? You say, I guess I'm going to have to do like this, -infinity to 0, and from 0 to infinity. Same is true for the range. It just doesn't include 0. So that's how you say everything except 0. It has no intercepts, no x or y intercepts. It does have odd symmetry. So the decreasing is interesting. So it's always decreasing here. It's always decreasing here. You see that? And it's technically always decreasing here as well. Well, wait. Yeah, it's always decreasing. So it's technically always decreasing. So we'll say it's decreasing, but we can't say from -infinity to infinity because it doesn't have a value for 0. So we'll say from -infinity to 0 and 0 to infinity. That's not including 0 though. Alrighty. Now, is it decreasing like at the same rate? Obviously not. It's changing, right? So like it's going fast like crazy here, but then it's still going down, but going down slowly. Okay. Anyhow, it's never increasing. It doesn't have a local min or max. It's no turning point, and it doesn't have an absolute min or max. Okay. Absolute value, and okay, we're almost done, I think. And then after that, my gosh, they're making us do greatest integer. I'm surprised. Okay, so absolute value function. Absolute value of anything is always positive. Absolute value of -2 is 2. Absolute value of 1 is 1. Absolute value of 0 is 0. 1, 1. It's just the v, guys. So it looks like this. It basically looks like the linear equation, but instead of continuing to negative, it bounces up like that. So that's the absolute value graph. Okay. The domain is all real numbers. However, the range starts at 0, including 0 to infinity, as you can see. Starts here and then goes up in both directions. The x and y intercept are the origin points. It has even symmetry, right? Symmetry about the y-axis. It's increasing from 0 to infinity, right? It's going up on the right side, but then it's going down on the left and going up on the right. So we'll say it's decreasing from -infinity to 0, and from 0 to infinity it's increasing. It has a local minimum at x equals 0, no local max, and has an absolute min at x equals 0, no absolute max. Okay, so it's very straightforward. So this is the constant function. A constant function is just the horizontal lines. says here, it's actually just asking you, these graphs will always be horizontal, I guess. It will always be a horizontal line with a y-intercept of b, right? Whatever that value is. So if it's like, if the equation is y equals 4, then it's going to be like 1, 2, 3, 4, right? It's the y-intercept that happens to be 4, but it's always, it's just horizontal at 4. That's all it means, okay? Alrighty. The greatest integer function, I'm surprised that's there. I'm confused by that, but it is what it is, right? So anyhow, the greatest integer function is always rounding down. So the greatest integer of -1 is -1. Of -0.5 is -1. It's always rounding down. -1. Excuse me. 0, 0, 0, 0, 0, 1, 1, 2, 2, 3, 3. So it looks like this. So it starts off here. You put a dot here and you put a line, circle. Dot here, line, circle. Dot here, line, circle. Dot here. It just looks like that. But don't worry too much about this. Not really sure why this is on there, but whatever. It's called the step function, that's true. Because it looks like steps, I guess. Okay, so let's continue. Alrighty, so now we're on to the different phase. So we did all the important functions. Notice that we did not cover a couple of them, right? We didn't describe the big ones that we're going to learn in chapter 6 is logarithm and exponential. These are very big. This is huge in chapter 6. And in chapter 5, we're going to do a lot of these, okay? A lot of those. So we're going to go over, and here's another example. So these two is chapter 5. So we're going to see a lot of that later. So although I'm not going to do this again, we're going to definitely see more interesting graphs, okay? Now, what is this part about? A piecewise function is taking an equation or a graph or whatever into pieces. So for example, if you're giving instructions and you're trying to put people in groups, like, okay, so these 10 people will do this, the other 10 will do that, and then the last 10 will do whatever, right? You're breaking the group into smaller pieces and you're describing what each piece will do. That's exactly the same thing is happening for equations, okay? A piecewise equation is when a function is defined by different equations, okay, on different parts of its domain. So, and that's called the a piecewise function. So these are the equation part. This is the equation part, and this is the domain part. And let me explain what this says. This says, this is what if I pick a number. Remember, when you're talking about equations, you're always asked to plug a number into x, right? It's always let x be 5, or let x be 100, or let x be -50, or whatever. It doesn't matter, but you're always plugging an x. What this tells you to do, this stuff on the right side, is telling you if you wanted to pick a number for x that's less than 0. Suppose I want to plug in -10. If x is less than 0, this is the equation I use. Okay? Remember how this works. Whenever you plug a number in, you can only plug it into one equation. You can't plug it into all of them. You can only get one equation for every plugging in. So what if I want to plug in 0? According to this, if you want to plug in 0, you plug it into this equation. Now the equation happens to be just a number, which means that's the answer already. But whatever. If you want to plug a number that's bigger than 0, like let's say 15 or 25 or 100, then you plug that number into this equation. That's how you interpret this, okay? So let's see if this makes sense. Find f of -2. In other words, let's plug in -2 to this equation. I'm going to erase all this stuff I wrote here, and I'm just going to look at the equation. If I want to plug in -2, which of these equations, we'll call it equation 1, 2, and 3. Which equation would I need to, would I be allowed to plug it into? Can I plug it into the equation 2 or 3? The answer is no, because -2 is less than 0. I can only use equation 1. So I plug it into equation 1. And that's it. Do not plug it into the other equations. You can only have one equation for every plug-in. -1 squared is 1. I'm done. How about f of 0? What can I do with that one? Well, according to the information here, I can only plug it into equation 2. And equation 2 is just an answer. We're done. We don't have to do anything. I'm finished. How about if I want to plug in 3? I want to plug in a larger number than 0, like 3. Which equation do I use? Well, according to the piecewise, I can only use equation 3. And you can only use one equation anyway. So the equation I can use is equation 3. So in this case, I'm going to plug in 3 into the x for equation 3. 3 plus 2 is 5. It's just that simple. Okay? Now, what's the domain of this function? How do you interpret the piecewise and figure out what the domain is? Well, you think about what it says here. Look at the first equation. If I plug in any number less than 0, or if I plug in 0, or if I plug in anything bigger than 0. Well, does that mean I can plug any number I want? Well, yeah. I can plug in negatives because that's less than 0. I can plug in 0 because it says it in the middle. And I can plug in anything after 0, anything bigger than 0. So I technically can plug whatever I want. In other words, the domain is infinite. Or we'll say that the domain is from negative infinity to infinity. Okay? Now, it says to graph it. Let me actually help you with this. I'm going to break this or divide this into pieces. When x is less than 0, that's this piece. This is the x-axis to the left of 0. I'm going to graph this equation, the quadratic equation. We just talked about this. We know what it looks like. It looks like a parabola. So it's going to look like this. Now, ironically enough, even though it says x has to be less than 0, you still start at this endpoint. So you plug in 0 into this equation. What's 0 squared? 0. So you circle it though. You do not shade it, you circle it. Because it doesn't actually equal. It says it's less than. But we still need to know the starting point. Now plug a number to the left of 0. Let's say negative 1. Negative 1 squared is positive 1. Negative 2 squared is positive 4. Negative 3 squared is positive 9, etc. So the graph looks something like this. A parabola. Whoop. It's a parabola. But it starts at 0, not including 0. That's why it's an open circle. And it goes to the left, right? To the left of 0. Now the second equation. The second one says it equals to 0. So where does that mean? That means when x equals 0, I'm going to graph this equation. No, that's just a dot. It's 2. So I put a dot on 2. Done. Now I graph the last one, which I'll do it in dark blue. This says when x is greater than 0. So I still plug in 0 into the starting point. I'm going to plug in 0 there. What's 0 plus 2? They say, oh, that's 2. So I don't technically shade it. I just circle it. And then I graph anything after. So after after x equals 0, like x equals 1. 1 plus 2 is 3. So 1 comma 3. How about when I plug in 2? 2 plus 2 is 4. So 2, 4. And so basically it looks like a line. Now you're thinking, wait a second. If all this was just one color, what would that look like? Because I have 3 different colors here. It'll look something like this. And then it'll look like that. Okay? So technically speaking, I don't have to have a circle and then shade in different colors. The reason why I did it different colors is because each of these different colors represent a different equation. And it represented a restriction on the domain. But it does end up looking something like that, right? Where this is like the y-axis and this is the x-axis. Ends up looking something like that. Not exactly perfect, I get it, but that's the idea, okay? That's what it looks like. Now that you see the graph, that's what C is asking us to do. Can we see what the range is? What's the smallest possible y value? You should say the smallest possible y value is this location here. Even though it doesn't include it, it would be 0 had it been shaded. So you say from 0, but not including 0 because it's not shaded. And then it goes up forever, right? Technically. So we're going to say to infinity. That's the range. Question E. Is this a continuous graph? Is it continuous on its domain? Meaning, can you draw this without ever lifting a pencil? The answer is no. If they were connected, let's say you saw this, then yes, this would be an example that you could graph without lifting a pencil. This is a connected graph. So, but this is not. The example here is not, so we'll say no, it's not continuous. And we're done. At least for that example. So we're going to move on to the next one. Okay, I like this one better. So the reason why I like it better is because you notice that the domain is not all the numbers in the world. And that's good that we get to see that. So we'll do that in a moment, but let's continue. So let's do A. Plug in -2. What is f of -2? Where can I plug in -2? There's 3 equations. Which equation can I use it? Well, let's see. Can I use it in the equation 3? We'll call this 3 2, 1. No, because I can only plug in numbers bigger than 1 into that equation. I can't plug it into this middle equation because that's only when x equals 1, which doesn't happen to be there. So if it's between -3 and 1, not including 1, I can plug it into the first equation. -2 is between -3 and 1, isn't it? So I use the first equation. So -2 times, and then I plug in -2 plus 1. -272 is 4, 4 plus 1 is 5. There you go, there's my answer. What is the answer when I plug in 1, f of 1? When I plug in 1, I use the equation 2, and it says the answer is 2. I don't have to even plug it in. They just give you the answer. What about if I want to plug in 2? Well, if you want to plug in anything bigger than 1, you use the third equation. And the third equation is x squared, so we're going to say 2 squared, which is 4. Done. Now, how can I determine the domain? We have to focus on this for the domain. Think of the smallest possible x value you can use. I can use -3, including -3. That's the smallest possible value. And then it goes from -3 all the way to 1, and then it continues on 1, and then it goes beyond 1, right? And it goes forever to the right. It never stops. It says when x is bigger than 1, so I can plug in 1 billion if I want. In other words, the domain continues to infinity. Now, how do you find intercepts? Well, without graphing it, you can actually find intercepts, okay? So I'm going to do the intercepts here, and then I'll put the answers in C, okay? So for the intercept, the first thing I like to do is, first intercept I like to find for piecewise is always a y-intercept, believe it or not. I always do x-intercept first, but not for piecewise. For piecewise, I always do y-intercept because it's so much faster. It's the easiest one out of the two. How do you find a y-intercept? You plug in 0 for x. So basically what I'm asking for is f of 0. Okay, let's look at the equation. Which equation can I plug in 0? I can only plug it into one of those equations. Which one allows me to plug in 0? It's not the third one, because the third one is only when I plug a number bigger than 1, and 0 is not bigger than 1. It's not the second one, because the second one is only if I'm using x equals 1, and I'm not using x equals 0. So it must be the first one, which is between -3 and 1, which is correct. So then I'm going to plug it in. By the way, sometimes it won't even have a y-intercept. If you cannot plug in 0, suppose it doesn't even, it says x is greater than 1, and that's it. There's no way x is less than 1. And you cannot plug in 0. Then it doesn't have one. It doesn't need to have one. It just, in this case, it does. We're going to use the first equation. We're going to say -2 times 0 plus 1. So -2 times 0 is 0 plus 1, so it's 1. So the y-intercept is 0, 1. So it says locate intercepts. I'm going to put the coordinate 0, 1. Okay. How do you find x-intercepts, though? It's a little trickier. To find the x-intercepts, believe it or not, you're going to have to write each of the equations. So -2x plus 1, 2, and what's that? Okay, the next squared. And what I'm going to do is, this is not necessary when I'm about to write, but I like to do it because it helps me. I like to put the mean for each equation. So for the first one, it's between -3 and 1. Now I'm going to put it in a box so I can know it's not part of the equation. I'm just writing out the domain so I won't have to keep going back and forth, back and forth. You know what I mean? It's just faster, and x is greater than 1. So that way I can just look at this. Now, what you have to do is for each of these equations, you got to solve for x by making them all equal to 0. So we're going to do all of them one at a time, okay? Let's start with this one. Let me solve for x for the first one. I'm going to go ahead and say, okay, -1, -1. I'm going to get -2x equals to -1. I divide both sides by -2. Good. X equals to -1 divided by -2 is just positive 1/2. All right, excellent. Now here's the question. Before I say that's an x-intercept, here's the question. Is this number, x equals 1/2, within that domain? If the answer is yes, then this is an x-intercept. If the answer is no, then this is not an x-intercept. So, is 1/2 in between -3 and 1? Yes, obviously it is. So then yes, this one works. So we're going to leave it alone. Perfect. How about this one? Well, there's not even an x to solve, so it has no x-intercept. There's nothing to solve. It's just 2 equals 0, which is not true. How about this one? Okay, let's solve for x. We're going to square root both sides. We're going to get x equals 0. Is the solution x equals 0 in that domain? Is x equals 0 a number greater than 1? You're going to say no. This is not an x-intercept. this would not be valid. So then I would say this is not an x-intercept. So it only has one x-intercept, and that's 1/2. Okay? And this x-intercept as a coordinate is 1/2 comma 0. Don't forget that. So we're going to go ahead and put that. We're going to say and 1/2 comma 0. That's the x-intercept. We're done. Now we're going to graph. So let's go ahead and graph. Now I hope by now you recognize that the first equation is a line. The second equation is just going to be a dot because it's 1 comma 2, right? It's just 1 point. And the third equation is going to be a curve. I hope you guys recognize that. So that way I don't have to keep explaining, certain things. So what I'm going to do is for the first equations, I'm actually going to plug in both endpoints. That's all I'm going to do. Plug in both. I'm going to plug in -3 into this equation, and I'm going to plug in 1 to that equation to see where the line begins and where it ends. I know it doesn't include the end, but I'm still going to know, I need to know where it's supposed to stop, even though it's not including it, okay? So I'm going to plug in -3 in here. So -2 times -3 is 6, and 6 plus 1 is 7, right? So -3 comma 7 is the starting point. Now I'm going to plug in 1. Even though it doesn't include 1, it's less than 1, not less than equal to. I still need to know where it is that it's supposed to sort of end, even though it doesn't end there. So I plug in 1 in here. -2 times 1 is -2. -2 plus 1 is -1. So when I plug in 1, the answer is supposed to be -1. I'm going to circle it. Okay? Oh my gosh, my handwriting's atrocious. There. I circle it because I want to make sure I realize, even though it goes from here all the way to here, it's a straight line, it never actually has a solid, it never gets shaded there. Okay? It's not perfect, but you guys get the idea. Now, the next one is a coordinate when x is 1, y is 2. I'll do that in this color. So there's a dot here when x is 1, y is 2. Perfect. And the last one, we'll do that in that dark blue. The last one is going to be x squared. So even though it doesn't include 1, I'm going to still plug in 1. What is 1 squared? You'll say 1, so we're going to circle 1. What is 2 squared? 2 squared is 4. 3 squared is 9. So the graph is that curve. Now I want you to see this picture and realize what I meant to say it did not have the x-intercept of 0 did not work. And I want to show you why. The graph of x squared was not allowed to continue until it reaches 0. Do you see that? It started, oh boy. It started when x was 1. Therefore, it did not have an x-intercept. That's why I had to scratch out this. I have to scratch out. That is not an x-intercept that exists on the picture. You guys see that? Notice that? What about the x-intercept here? Yeah, it does. It has an x-intercept right there at 1/2 comma 0. And the y-intercept, it's not a perfect drawing, but the y-intercept is at 1, at 0 comma 1, which I think that's what it was, right? Yeah. You see? It's very important you see that. So now what's the next question? The range. Well, let's look at the range. The smallest y value is -1, and then it goes up it doesn't stop at 7. This arrow means it goes up forever. So it's from -1 to infinity. Even though it doesn't go up forever in this green line, it still can go up forever on the blue line. So there's going to be a y value somewhere, everywhere else, right? So we're going to say from -1 to infinity. Does it include -1? No, it doesn't. It's an open circle. So not including -1 to infinity. Is it continuous? I think it's pretty clear it's not continuous, okay? You guys can see that you cannot draw that without lifting a pencil. It's impossible. Okay? Alrighty. Last question, I think? Yeah, that's what we're at the last point. So let's continue. So in May 2018, Commonwealth Edison Company supplied electricity to residences for a monthly customer charge of $7.58 plus 8 cents per kilowatt hour for the first 400 kilowatt hour supplied in the month, and then about 6 cents per kilowatt hour for all usage over 400 kilowatt hour in the month. Okay, what is the charge for using 300 kilowatt hour in a month? Let's see. The first 400, they charge you this much, but they also charge you 7. So they kind of like, okay, so they always charge you $7.58, but then they also charge you 0.08 $3.275 per hour for the first 400. So since 300 is within that, I can say just multiply by 300. Okay. Definitely need a calculator for this one. 0.08. What is it? 275 times 300 is 24.825, and this is 750. Oops, 758. So I'm gonna add plus 7.58. It gives me 32 and okay. So I'm gonna round to obviously to pennies. I mean, I'll just put the answer. It says 32.405. No, they're gonna make you round, so which is approximately $32.41, right? They're not gonna, make you write it that way. All right. So then, what's the charge for using for the first 700? Okay, that's trickier. For the first 400, they're gonna charge you 8 cents, and then after that, they're gonna charge you about 6 cents. So that means that you're gonna have to do this: 758 plus 0.08275 times 400. This is for the first 400, and then plus 0.06208 for the next 300. So that way the 400 plus 300 is equal to the 700. All right. So I'm going to put all this in my calculator in one giant. So 7.58 plus 0.08275 times 400 plus 0.06208 times 300. The answer it gives me is 59,304. So it gives me 59.304, which is approximately $59.30. We're going to round it. Okay. Alrighty. Next. So notice how I did the first 400, sorry, and then the next 300. So the first 400 and then remaining 300. Okay. They were at different rates. All right. If C is the monthly charge of X kilowatt hour, whatever, develop a model relating the monthly charge of kilowatt hours used. This that is express C as a function. Okay, so this is going to be a piecewise because C is a function of X, right? So let me put C of X equals, and I'm going to have a piecewise. So you can't have negatives. It doesn't make any sense, right? So you're going to pay $7.58 plus 8 cents, or almost 8 cents, 8275 times X for the first 300, right? So if X is between 0 and 300. Make sense? However, what happens if X is bigger than 300? Well, what do you pay? Well, this is a little tricky. So it's going to be the following. You have to first figure out how much you pay for the first 300, and then you add, like we did here, for the first 400. Did I say 300? I'm sorry, guys. This is the first 400. I noticed it because I wrote it here. And then after that, it's after 400. Okay, so for the first 400, and then you add the rest of it for the remaining. So how much would this cost? I actually didn't do that separately, so let's see. It's going to be 7.58 plus 0.08275 times 400. It's going to actually be 40.68. This is for the first 400 plus the remaining 0.06208. Now I don't put X here. I'm going to put X minus 400. You're thinking, why am I doing that? The reason why I have to put minus 400 is because if I ask you to figure out how much I'm going to pay at 500 kilowatts per hour or whatever, then I'm going to have to plug in, I'm going to have to add the 4868 for the first 400 and then this for the next 100, because I said 500, right? Well, how do you get the next 100? You subtract the first 400. The first 400 is already represented in the first half. So that's why I had to put X minus 400. Now, if you wanted to distribute this, you can and simplify that, but I'm going to leave it like that. I'm going to say this is the answer. I remember the homework question, if I'm not mistaken, because I've done it so many semesters already. They're going to require you to distribute this, but yeah, they're going to require it. So this wouldn't be technically accepted in homework, but whatever. You guys get the idea. So alrighty, I think that was that was the last one. So I hope this made sense. I know it was a lot of interesting and new stuff. So if you have any more questions, let me know. If not, we'll see you for the next one. Take care.